All right. Good morning, folks. Welcome back. Let's go ahead and let's get started and let's pick up with where we left off yesterday. I'm trying to make sure that we try to get started with the discussion of limiting reagents today, because that's going to take us a little bit of while. We'll take us a couple of few lectures to practice doing to understand how to work out those problems. Okay. All right. So we left off with the discussion about how we can do a second type of stoichiometric calculation. Now remember, stoichiometry is basically an examination, an analysis of a chemical reaction. Specifically, we're looking at the quantities involved in a chemical reaction, the amounts of reactants, amounts of products, and we're comparing them to one another. And we're trying to analyze to see how much one component of reaction that we need if we change the amounts of another component of that particular reaction. So that's the essence, excuse me, that's the essence of stoichiometry, an examination of quantities involved in a chemical reaction. Okay, so we were able to do a couple of different types of stoichiometry, stoichiometric calculations, one involving moles, the second involving masses. And so we were examining the masses and the moles involved in a chemical reaction. And we saw then that with moles, that conversion was essential. We need to do that moles to moles conversion because that's what we're able to do correctly from the balanced equation. We can take the coefficients from the balanced equation, get the mole ratio that we need to convert between moles and moles. Okay? Now, but it's not practical in the sense that if we were to carry out the reaction, if we were to run the reaction, it's not practical because we can't measure out moles. And so what did we have to do? We had to figure out a way to obtain masses from that balanced equation as well. So we could not get that directly from the balance. We can't get those numbers directly from the balanced equation. We don't have a mass to mass ratio. And so we had to kind of go a roundabout way, and I had given you that flow chart to help you do that. But the process only involved including and using two other conversion factors that involve two different molar masses. Okay? And so we learned about molar masses back in chapter 10. And so we're incorporating that into our understanding of stoichiometry. So the mass to mass conversion, the comparisons of the two masses involved, or the masses involved in a chemical reaction, involves three conversion factors. Okay? Two of them are molar masses, and the last one, the third one that we have to use is the mole ratio. Okay, and so that was the mass to mass conversion, and that's typically what we do in lab when we carry out these calculations. We do a mass to mass conversion. But I pointed out to you then that we can also do other types of comparisons as well. We can also determine other types of quantities involved in a chemical reaction and thus do other forms of stoichiometric calculations. We're not limited to just masses. We're not limited to just moles. Let's say, for example, we wanted to find out the number of molecules involved in a particular chemical reaction if we start out with, say, mass here. So this is a mass to molecule conversion. And so I wanted to do this, and we'll do a volume to volume conversion as well, to show you then that stoichiometry can incorporate any type of quantity. We can include and we can calculate any type of quantity involved in a chemical reaction. Now, would this be a practical calculation to do? Meaning, would we do this calculation in order to carry out the reaction? No, we would not. What we would use this particular calculation for is that if we wanted to determine then the number of particles involved in the chemical reaction for other purposes, we can do that. We can do this calculation. And so the calculation involves a very simple, involves a very simple conversion, okay? And the method, the technique, the process by which we do this conversion is exactly the same way we did the mass to mass conversion. And that's what I wanted to point out to you. And that's what I want to make sure I get you to understand at the end of this particular calculation. Okay? So what I needed you to do, and so go ahead and pause the video right now and go get your work from yesterday, the one that you submitted at the end of the period yesterday, and the one in which I asked you to find the molar mass of water and the mole ratio that you would use to carry out this calculation, and then the final conversion factor that you need to get this done. So go get that paper and let's compare our answers. Okay. All right. So let's go ahead then. Let's take a look at what we have. Okay, so first of all, okay, the molar mass of water should be simple. So the first one is molar mass of water, just 2 hydrogens, 1 oxygen. Then the molar mass of water is going to be 18 grams per mole. Okay, so that's what we're going to use first. Okay. Now the mole ratio here. Now, if you take a look at this, the conversion. Now remember, all stoichiometric calculations are conversions. And so you ask yourself 3 basic questions. Okay, so when you ask yourself the 3 basic questions, you will find then the mole, essentially the mole ratio that you need. Because look at this here. They tell you that we are given to start out with 29.2 grams, though 29.2 grams, but 29.2 grams of water. Okay, so that's what we want first. So we have that. They're asking us, so what are we solving for? They're asking us to find the number of particles of oxygen. So there is the second component. So that's the second part of the reaction, the calculated part of the comparison we're doing. And so the mole ratio, whatever the mole ratio is we're going to use the mole ratio between water and oxygen, because those are the 2 components of this reaction that we want to examine. So that's how you would be able to determine what mole ratio you're going to use without having to write out everything else. Okay. All right. So right now then we have this we're going to use. Okay. We'll plug it in just a moment, but we know then that for every 2 moles of water, we will produce 1 mole of oxygen. And so the mole ratio we're going to use is either going to be 2 moles of water over 1 mole of oxygen, or we'll use the reciprocal of that. So this is the mole ratio that we're going to use. Okay. All right. And so if you take a look at this, then the molar mass we'll use first, because this is mass. So we'll set that up. Okay. So what's the only missing conversion factor here? What's the only missing one here? Well, we need one that includes molecules here. Okay, and we have that. Okay, and so remember then, we said then that a mole of a particular substance, and since we're solving for oxygen here, we're going to use oxygen here. 1 mole of oxygen is going to be equivalent to 6.02 times 10 to the 23rd molecules of oxygen. And there it is. There is the third. And so we'll set this up as a conversion factor. Okay. So we'll write in the fraction. I've run out of room here, but we'll write in the fraction to take advantage of that relationship. All right. So there it is. We have what we start out with. We have the amount of water. We have what we're solving for, which is the molecules of oxygen, and we have all of the conversion factors that we'll need to use right here. So let's go ahead and let's set up this problem and get it done. Okay, so let's start out then. So we were given to start out then 29.2 grams of water. Okay, and we're going to go ahead and we're going to solve for molecules, and I'm going to write it here. So molecules of O2. Okay, so we need to find that number. Let me give myself a little bit more room here. Okay, and then we end up with the big number. Okay, and then we'll plug in the conversion factor. Hopefully you recognize then that the very first conversion factor we have to plug in is going to be the molar mass of water, and we will divide by the molar mass of water, which is going to be 1 mole of water over 18 grams of water. Okay, hopefully you see that that will allow us to cancel out grams of water. The next one's going to be the mole ratio here. And hopefully you're going to see then that we're going to use the reciprocal of this because we need moles of water on the bottom. So we'll have then 1 mole of O2 over 2 moles of water. Okay, very good. And then finally then we need to use the Avogadro's number here, and hopefully you see then that we're going to have Avogadro's number on the top, 23rd. And I can't fit the word molecule in there, so I'm just going to write down O2 for every 1 mole of O2, but hopefully you get the idea. It's molecules of water. Okay? And that's it. That's it. That's how we set it up. And so therefore, if you set it up correctly, you punch it into your calculator, then you'll get your answer. Then it's 4.88 times 10 to the 23rd molecules of water. That is stoichiometry right there, folks. So the stoichiometry involving stoichiometric calculation involving masses and number of particles. Okay? All right, very good. What I'd like you to do then, let's practice this. Let's go ahead and let's practice this here. Okay, and want you to do number 18 in your problems. It take about 5 minutes, okay? Work out this problem here. I know the homework, the set B involved these calculations as well. So if you didn't get some problems done because you weren't quite sure how to do it, now that we've worked through a few of these here, go back and try to get them done, and then see if you get the answer. If not, then like I said, please come by and see me. I'll be here today after school, 1:30 to 2:30, or come by on Monday after school, 1:30 to 2:30 to get your questions answered. But let's go over this one here. Let's go ahead on your paper. Okay, so on your paper, work out this problem here. And then when you get back, we'll work it out together. Okay, and then you compare your answer, compare your work with the work that we're going to do here, and make sure that you find then whether you got it, whether you did it correctly or not. And if you didn't, make sure you find where you made your mistake, and then correct it on the homework. Okay. All right. So go ahead, work out this problem, and then we'll work it out together. Okay, 5 minutes. All right. Let's go ahead then, and let's work out this problem together. Let's take a look what we have here. So again, let's start out balanced equation first. Let's go ahead and write that out. Okay, so hopefully you were able to balance out this equation here, folks. So it's going to be 2 potassium chlorates, KClO3, decomposing to form then 2 potassium chlorides and 3 oxygens. Okay. All right, so 2, 2, 3, that's the balanced equation there. So hopefully you got that. So next step then is identify what you start out with, okay, what you're going to solve for, and then identify the appropriate conversion factors that you'll need in order to get this done, okay? So let's go ahead then. So we were told that we have 6.54 grams of potassium chloride. So let's write that in. We have 6.54 grams of this compound to start out with, okay? They want us to find how many molecules of oxygen. So we're converting between the conversion here. Okay, so if we start out with 6.54 grams of potassium chlorate, we want to find then the molecules of oxygen. So we want to calculate for the molecules of oxygen. So there's our conversion. What do we need then? Let's go ahead and write down the conversion factors that we need. Well, first of all, we need the hopefully you wrote this down, or if not, you can just again, I'm going to list it here for you, but again, at some point, hopefully you can just go ahead and set up the calculation and get it done. Okay. So when you show the work, I won't need you to list all of the conversion factors, but I want to do it here for you so that you can see where we get this. Okay, so we need the molar mass of KClO3 first. Okay, so the molar mass of KClO3 is going to be, I have here 120, when I did it, I used an extra decimal place here, 122.6 grams per mole. Okay, so we need that to do this conversion. We also need the mole ratio, folks. Okay, so what's the mole ratio that we'll need to do this problem? Well, it's going to be the mole ratio between potassium chlorate and oxygen. It's going to be the 2 to 3 mole ratio. And I'll just write it out here. And again, I won't write out the reciprocal, but understand that we can have that as well. So it's going to be 2 moles of KClO3 over 3 moles of oxygen. Again, we may have to use the reciprocal, but for right now, we'll just write that in. Okay. And then finally, the last conversion factor, then it's going to be Avogadro's number. We need Avogadro's number. Why? Because we're asked to find the number of particles. Okay, so that means then it'll be 1 mole of oxygen over 6.02 times 10 to the 23rd molecules of oxygen as well. So, and again, we may have to use that reciprocal in order to get the calculation done. So there it is, folks. Those are all of the conversion factors. We've answered the question, all 3 questions. This is what we start out with. This is what we want to solve for, okay? And there are the conversion factors to get us from start to finish. Okay, so let's go ahead. Let's work out this problem. Okay, so we start out with then 6.54 grams of KClO3, potassium chlorate. Okay, and we want to find then molecules of O2. Okay, first conversion factor then, molar mass of potassium chlorate, which we're going to divide, which is going to be 1 mole on top, KClO3, for 122.6 grams of KClO3. Second conversion factor then is going to be the mole ratio here. And here, hope you recognize then that we have to use the reciprocal, so not 2/3, but 3/2. So it's going to be 3 moles of O2, 2 moles of, I'm sorry, KClO3. Let me write that in the bottom there. And then finally, Avogadro's number, 6.02 times 10 to the 23rd molecules of O2 over 1 mole of O2. Okay. All right, so hopefully you can see how we set that up, and you were able to set that up as well. And if you set it up correctly here, you punched in all the numbers correctly in your calculator, you should end up with your answer then, and hopefully you did. 4.82 times 10 to the 22nd molecules of O2. Okay. All right, so hopefully you have that down, and compare your answers. Now make sure you write down what we have here and see what you did, okay, and compare with what you did. Okay. All right. So let's go on then. And so again, calculating for the number of particles of a compound is useful and in theory, but we don't actually make use of it in the lab. Okay. However, we saw then that we can use masses. We can calculate for masses, and we can measure out masses and then use those masses in our lab. We can also measure out volumes. We have measuring tools. We have measuring devices that can measure out volume as well. And so what we want to be able to do then is we want to be able to do a calculation, a stoichiometric calculation involving volumes. We want to do this volume to volume conversion. And the volume, the calculation here will involve specifically then gases at room temperature. Because typically with liquids and gases, it's easier to deal with volumes than it is with masses. Okay? And especially with gases, because gases, remember we talked about this, gases are so, they're the least dense state of matter. It's easier for us to measure volumes of gases than it is to measure out the masses of a gas. So with that said then, we will typically do this calculation. We will do this calculation for reactions that involve gases. Okay, so if you have the volume of one gas in the chemical reaction, and you want to find then the volume of a second gas in the reaction, can you do that? Well, if the conditions are at STP, standard temperature and pressure, which is, remember again, 0 degrees Celsius and 1 atmosphere. If that is the case, then we can do this conversion, but we cannot do it directly. Just like with all the other conversions we cannot do that directly, not from the balanced equation. We can't get the numbers directly from the balanced equation, the ratios to get that done. Okay, so we have to go ahead and just like with the other calculations, we can do the mole to mole conversion, okay, because we just need the mole ratio. And so the question then is, if we start out with volume and we need the moles, and we start out the volume for the first gas, okay, can we obtain the moles of that first gas? And obviously the answer is yes. We can use the molar volume. Remember the molar volume at STP is 22.4 liters for every 1 mole. So we can go ahead and do that. Once we have that, and so make sure you understand that what we're going to do here is we will divide, just like what we did earlier. Okay, we will divide by the molar volume here. Okay, so this will be the first step in our calculation. Okay, and so once we divide by the molar volume, we'll have the moles of the first gas. Okay, we can identify the mole ratio, and this would be our second calculation. Okay, to get to the moles of that second gas. Now the question then is, because we don't want just moles, we want to be able to get the volume. Can we do this last calculation here? And again, that is, can we convert between moles and volume? The answer is obviously yes, because we know what the molar volume of that gas is. And in this case here then, what we would do then is we would multiply by the molar volume, okay? So if you notice then, we are going to use 3 steps here as well to do this stoichiometric calculation. We will not do it as 3 separate steps. We're gonna just identify the conversion factors, and there we have it. We have all 3 conversion factors. Since we have it there, we'll plug it into one long conversion factor and get it done that way, okay? And so we can do this calculation then. We can do this calculation as long as we know that it's a gas at room temperature. Okay? I'm sorry, at standard temperature and pressure. Okay, so let's go ahead then And let's work out. Let me go ahead and ask you now to have this. Okay? To finish up, then, what I'd like you to do with this particular problem, just like what we did yesterday. Okay, to finish up here, this is what I would like you to do. Okay, on your paper, and so this will be for Monday. This will be for Monday. What I'd like you to do then is find the mole ratio. What is the mole ratio that you'll need? So read this problem here. So identify the mole ratio that you'll need to do this calculation. Okay, and and so with the that said, then what else? What other conversion factors? What other conversion factors are needed? Okay, what other conversion factors are needed to get this particular conversion done? So for Monday, please have these two. Have it written out on your paper. You already have that paper where you did the previous problem. So on that paper that you're going to submit today at the end of the period, go ahead and write down the mole ratio and the conversion factors that you'll need to work out this problem. Now, if you can work out the problem, folks, if you feel comfortable working out the problems, by all means, work out the problem, and then we'll work it out on Monday. We'll compare answers, but please make sure you work this out. And then what we'll do then is on Monday, it looks like we're done with the stoichiometry, with these basic stoichiometric calculations. We'll start limiting reagents on Monday to help us to work through that discussion of limiting reagents more effectively and more efficiently. Please make sure you take a look at section, I think it's 12.3 in your book. Scan it really quickly, folks, and then just make sure you know what it's about, so that on Monday we can start a discussion of limiting reagents, and hopefully I can go a little bit faster in order to get that done. Okay. All right. So with that said, make sure you get this done, folks. Have a good weekend, and I will see you on Monday.